In this episode of Remote Calculus, we will be doing epsilon delta proofs. Epsilon delta proofs are sort of like Shakespeare to an English literature class. They are a foundational part of the idea of limits. And just like in an English literature class, you should get some exposure to Shakespeare. If you really like Shakespeare, you could read the whole collection. If not, at least you have gotten some of that foundation. Same thing with epsilon and delta proofs. You should get some exposure so that you understand the premise of proofs, you get exposed to some of the notation, what absolute value really is useful for and what it really means comes up in these proofs. If you really like these proofs, then you can take a lot of more upper level math classes where the ideas are more abstract and theoretical and everything is really about the explanations. So we're going to be doing a couple of proofs. One will be find the limit as x goes to 20 of the line 5/2 x minus 10 and show that it equals 40. In terms of our previous discussion of limits, we know we can just plug the 20 in, a line's a continuous function, plug 20 in, you'll get 40. There you go, you showed the limit was 40. That's not what this activity is about. It's about defining epsilon and delta. So what you're really doing when you are pointing out what a limit is you are showing that for any small tolerance around your limit value, in this case 40, you would be able to find a tolerance around your special x value, 20, such that if you stay within that tolerance of 20, all of your f of x values stay within your chosen tolerance of 40. I know that's a mouthful, okay, so let's kind of repeat it. We're wishing to show that for some small tolerance, which we're going to call epsilon, around 40, we can find a tolerance delta around 20, such that for all values within delta of 20, you compute f of x values that are within epsilon of 40. So as long as I stay within a certain amount of 20, I will always stay within my set boundaries of 40, where epsilon is your set boundary. For example, choose epsilon to be 0.05. I want to stay within 0.05 of 40. I don't want to go outside of 40.05 or below 39.95. So we're trying to keep the distance between our function and 40 less than 0.05. That's what absolute value really is. The absolute value of this difference is the distance between f of x and 40. If you take the absolute value of just a number, you're really taking the distance between that number and 0. So in this case, we want the distance between f of x and 40 to stay less than 0.05. Well, my function was 5/2 x minus 10. So replace f of x with 5/2 x minus 10, and then I'm subtracting 40. That's what we want to stay less than 0.05. Negative 10 minus 40 is negative 50. If I factor out the 5/2, I get the absolute value of x minus 20 as the other factor. Notice 5/2 times 20 will be 5 times 10 or 50. So when I factor out the 5/2, I'm left with the absolute value of x minus 20. But hey, the absolute value of x minus 20 is the distance between x and 20. That is my tolerance around 20. Like that expression means the little tolerance that I'm going to stay within 20. So I can actually replace the absolute value of x minus 20 with my symbol delta. So then let delta be 0.05 divided by the 5/2, okay, because this is delta, this is 5/2, this is equal to the function that we want, or sorry, it's equal to the function minus 40, and we want that to stay less than 0.05. So that's where we're coming up with this, okay? We're dividing the 0.05 that we want the difference less than, we're dividing it by the factor 5/2. You get 0.02 for delta. So that means that f of x minus 40 which we already showed was equal, again the absolute value of, which we already showed was equal to 5/2 times the absolute value of x minus 20, but the absolute value of x minus 20 is delta. For our example, delta would be 0.02. So when I pick x's so that their distance from 20 is less than delta, the distance of the function from 40 is going to be less than 0.05. So for example, if delta is 0.02, then I have to pick x's in between 19.98 and 20.02. 19.99 will be an example. 19.99 falls in that range. So plug that x into your function and you get 39.975. 39.975 is less than 0.05 away from 40, so it works. And I just picked 0.05 as a number to pick so that you actually had a number to look at, but epsilon could have been any small value. And delta would then be epsilon divided by that other factor of 5/2. That's always going to give you a tolerance around your special x. We often call that special x a, and our limit as x goes to a. That will always work as a tolerance, and your y values will stay within whatever tolerance you picked for epsilon of 40. In terms of a picture, this means that, so here's my line, that was my function, here's 40. Epsilon is a tolerance around 40, so it's how much I can go above 40 and how much I can go below 40. Delta is the distance from your input, so 20 was our special input. It's how far away you can go from that input and stay within epsilon of your goal, your limit. So in this case, like the example we gave, when epsilon was 0.05, delta was 0.02. But we could have picked any epsilon. I could move these two lines closer together and my delta would just get smaller. And how we would find delta is delta would end up being whatever epsilon we picked divided by the 5/2. That would be what we could use for delta. So we have proven that the limit really is 40 when we plug in 20 by using this idea of tolerances. Let's do another epsilon delta proof example, this time not with a line but with a quadratic polynomial. We're going to complete an epsilon delta proof that shows that the limit as x goes to 8 of 4x squared minus 9 is equal to 247. So we wish to show that for any small tolerance that we're going to call epsilon, epsilon's going to be the tolerance around the output. So our output is 247, that's what we're trying to hit. So for any tolerance around 247, if we can show that there's always going to be some tolerance around 8 that's going to work, such that any x value that's within that tolerance of 8 computes f of x values that are within epsilon of 247. Again, epsilon is the tolerance around the output, delta is the tolerance around the input. For example, we could pick epsilon to be 0.02. If that were the case, then we would want the distance between my function and 247 to be less than 0.02. My function is 4x squared minus 9, so I'm replacing f of x with 4x squared minus 9. If I clean up 4x squared minus 9 minus 247, I get 4x squared minus 256. Notice I can factor a 4 out, and that gives me 4 times the absolute value of x squared minus 64. But I can factor the x squared minus 64 as x minus 8 times x plus 8, and rules of absolute value says that the absolute value of a product is equal to the absolute value of the individual factors. So I can put absolute value signs around the two factors. The absolute value of x minus 8 is the distance between x and 8. That is what absolute value means. It means the distance between two things, in this case x and 8. That is my delta. Delta is the tolerance or the distance you can move away from 8. So replace the factor absolute value of x minus 8 with delta, and then we have that the difference between the function and 247, again in absolute value, is equivalent to this. And then consider how we're taking the limit as x goes to 8. If you're taking the limit as x goes to 8, it means you're plugging in numbers that are close to 8. I'm not plugging in 5,280. I'm not plugging in negative 306. I am plugging in numbers like 7.999 or 8.01. So the absolute value of x plus 8 is somewhat bounded, since we're not straying very far away from 8. So you could think about how the absolute value of x plus 8 is going to be kind of close to 16. And then 4 times that is going to be kind of close to 64. So why don't we just consider that this 4 times the absolute value of x plus 8 is going to be less than 65, because we know it's going to be close to 64. And as you crowd in towards 8, the closer it's going to be to 64. So on that note, the difference between the function and my limit should be less than delta times 65, because we know 4 times the absolute value of x plus 8 is going to be less than 65 by the time we get really close to 8. Then let delta be epsilon divided by 65. Our example epsilon was 0.02, so we would take 0.02 and divide by 65. That's how we would get our delta tolerance. If you pick x's so that they stay within that tolerance of x, then that's going to force the difference between the function and 247 to be less than epsilon, because here's the function minus 247, that's the absolute value of it, and it's equal to epsilon times some product we know is less than 65. If you pick delta to be epsilon divided by 65, and you're multiplying that by something less than 65, then this difference has to be less than epsilon. There is our proof. We've completed the proof. We showed that definitely there's a tolerance delta that's going to work. Plugging in some numbers to just see what's going on. If epsilon really was 0.02, then that means we want our function value to stay between 246.98 and 247.02. And delta then is epsilon divided by 65. If you added and subtracted delta from 8, then you would get an upper bound of 8.0003076 approximately, and a lower bound of 7.9999692 approximately. And pick a number that's in that. So for example, 8.0002. 8.0002 falls in this range. When I plug that into my function, remember the function was 4x squared minus 9, I get 247.012. Well, that is within epsilon of 247. It is less than 247.02. Pick another number that's in that range, 7.9999. That falls in that range. If I plug it into the function, I get 246.9936. That's greater than the lower bound of 246.98. And so again, it falls within epsilon of 247. So as long as I pick numbers within delta of 8, I will get y values within epsilon of 247. And again, there was nothing special about the 0.02. This is going to work no matter what small value you chose for epsilon. Again, it should be a positive number because you're talking about a distance. Distances are always positive. And then if you use delta equal to epsilon divided by 65, that will work. I do want to point out that there was also nothing really special about the 65. You needed to pick a number greater than 64, okay, because the boundary of 4 times the absolute value of x plus 8 was 64. So any value greater than 64 would work as the denominator here. Now in terms of our picture, it's a little bit hard to see this because that delta is so small, but here's the 247. Here's epsilon equal to 0.02, gives us an upper bound and a lower bound, and the boundaries around 8 are hitting it here and here, okay? So delta is the smaller of those two distances, and it is, you know, in this case it was 0.02 divided by 65, so it's approximately 0.0003 something. But it's the distance from 8 to the boundary, so that any number, if I go on the positive or the negative side of 8, I stay within these boundaries of 247. So that's a little introduction to epsilon and delta. Again, epsilon is the tolerance around the output, delta is the tolerance around the input, and another important thing that came out of this is that absolute value as a notation means the distance between x and your other number, or f of x and your number. So absolute value means distance between two items that are being subtracted.